Hello. This bit is on what is called the Gauss's lemma. So Gauss is everywhere. And its application to figuring out when a polynomial is irreducible. Over the rationals. So let's start with the lemma. What it says is the following. Suppose that we have an integer polynomial. Let's call it u, which means that the polynomial just has integer coefficients. Then the lemma says that it can only factorize over the rationals if it factorizes over the integers. And moreover, the factorizations are related in a very strong way. So let me assume that it factorizes over the rationals, that there are polynomials f and g which in the product give u, and f and g have rational coefficients. So let us have this all, and then the lemma says that there is just a rational number over S, such that if we multiply over S with our f, we will have an all integer coefficient polynomial A. And if we multiply S over R with a polynomial G, we will have again an all integer coefficient polynomial called B. And obviously u will still be factorized, but now into all integer coefficient polynomials A and B. So that is the statement of the lemma. That's what we're going to argue for. And the argument is, well, very simple, but yes, it's somewhat interesting. Let's look at how it works. So start with polynomial f, and it has rational coefficients. So let's look at the coefficients and namely at the denominators of the polynomial f. So let's produce a number. Let's call it df. So the number will be the greatest common divisor of all denominators of coefficients, all the coefficients of f. And the property of this number is that we multiply it by our polynomial, and the result will be all integer coefficient polynomial. We just clear the denominators in f. And the same way, analogously, we define the number, by the way, it's an integer. We define the number for g, again it will be an integer number, defined this way as the denominator of all the coefficients of g, and the immediate property will be if we multiply g with this number, we will have a polynomial with integer coefficients. So let's take the product of these two numbers, call it d, and then multiplying our u with this, it's as good as multiplying f with its GCD and g with its GCD of all of the denominators. And those are integer polynomials. Let's call them a prime and b prime. So this is a prime of t, and this is b prime of t. Yeah, we spoiled a little bit our u. We scale it up by some integer, but then we get these two integer factors in it, which really are just scalings of the original factors f and g. So what we're going to do now, we're going to look at d as an integer, factorize it into products of primes. Really, we just have to take out one of the primes which sit in the factorization. So let's just factor it into a product of a prime. and yeah, something else, everything else. And then let's look at what this factorization will turn into when we reduce mod p. So now we will look at this equation but reduced mod p. We will look at coefficients which are integers mod p. So in this polynomial ring we will have the equation that 0, because p divides d and that side will become 0, is equal to the reduction of the coefficients in a prime and then the reduction of the coefficients in b prime. So those polynomials multiplied will give us 0. Well, how can we get 0 in the polynomial ring? Coefficients reduced mod p still form a field, and so this polynomial ring doesn't have 0 divisors. Non-trivial 0 divisors. Either a prime or b prime reduced will have to be 0. So just let's fix aside, assume that a prime reduced is 0. Well, what does it say? It says that a prime is all a multiple of p. All the coefficients are divisible by p. So we can factor a prime as some other polynomial times p. And now let's bring it back to this factorization. Let's look what it says. So p divides d, and the division statement is that d is equal to p times d prime. That is on one side. On the other side we have, we chose a to be divisible by p, so p a double prime of t times b prime of t. This is not the derivative, by the way, this is just a polynomial. So this product is equal to this. And then we can just cancel p out and reduce d to d prime. And still have the factorization into a product of two integer polynomials. So that is a step of induction, doing it iteratively, taking a prime out of d prime now and reducing it further. We will continue until we have to stop. We cannot continue forever. D prime or d is just an integer, so it has only finite number of primes in it. So that repeated will give us a factorization. When we run out of primes in d or d prime, we will have a factorization into some integer polynomials. And in the process, all we do is we scale or divide one of those by a prime. So we will be dividing one of our polynomials by a prime and iterating and ending up with this product. And that is exactly as predicted by the statement of the lemma. So we get our integer coefficient polynomials a and b as scalings of f and g with some rational coefficients. So effectively, again, Gauss's lemma says that if we have a factorization of all integer coefficient polynomial into a product of two rational polynomials, then effectively the coefficients can be made integer of those factors if we just multiply by one of them by rational number and the other by the inverse of this rational number. So that is it. That is the end of the proof. Let's look at applications of this lemma to a practical problem of figuring out when a polynomial is irreducible over the rationals. And the easiest polynomials are small degree. Then irreducibility or reducibility is somewhat determined. So for example, we have quadratic polynomial, or something like that, t squared minus t plus 1. That's a polynomial with integer coefficients. That's an important condition for the Gauss's lemma to be applicable. And if it factorizes over the rational numbers, Gauss's lemma says that it should also factorize over the integers. So let us assume that this is not irreducible. This is a reducible polynomial, and factorize it over the rationals first, but then it has to factorize over the integers, so it has to be a product of two linear terms. And we can make them monic as well. So starting with a monic polynomial, and we'll assume that they are also monic. So something like t minus a, t minus b, a and b will be roots. Of course, we could check, knowing possible a and b's, if they are roots or not of this concrete polynomial. But let's look what a and b, their integers by Gauss's lemma, what they have to satisfy. If we just open these brackets, multiply the terms, the free coefficient will be the product of a and b. And since they are integers, they will have to be divisors of 1, so they will have to be themselves 1 or negative 1. Neither 1 nor negative 1 works as a root. And so this factorization is impossible. And so this polynomial is irreducible over the rationals, but by Gauss's lemma is also irreducible. Sorry, over the integers, but by Gauss' lemma says that it is also irreducible over the rationals. Let me finish with one more example of degree 3. Something like this. So this polynomial is still, if reduces, it has to reduce into a product of a linear term and a quadratic. And again, we can assume that the leading coefficients are 1. Again, they have to multiply into 1, so they have to be themselves plus or minus 1. So we can make them both 1. And then a will have to be a root, so you could check, knowing a, that it is a root or not. But what do we know about a? Well, still we know that negative a times c is negative 2, so a times c is 2. And again, by Gauss's lemma, we can assume that a and b and c are all integer numbers. So a, as it is a divisor of 2. So a has to be plus minus 1 or plus minus 2. And direct checking shows that neither plus minus 1 nor plus minus 2 are roots of this polynomial, and so this polynomial is irreducible because this factorization is impossible. So that's it. See you